Thanks. I hope there's still some applause left at the end. So I think possibly relevantly, I spend a lot of time writing testing tools and a lot of time using testing tools. And so testing has kind of been a big part of thinking about how we do continuous deployment. So the 1,000-foot view. We take a reference image from Fedora, SUSE, Debian, wherever, and we can get three basic outputs from it. We can, actually, I should probably ask a couple of questions and set up some basic expectations. Questions from you along the way are fine. We're probably going to run out of time, so there's no point saving them up for the end. Who here is familiar with AWS, OpenStack, cloud sort of technologies? Right, the few of you who didn't raise your hand may be out of luck, sorry. Not that I'm going to try and avoid it, but we're going to have to sort of assume some basic knowledge as we go on. So an AMI, ARI, AKI triple is a machine image, a RAM disk image, and kernel image. It's an Amazon format for uploading software to run in their virtual machine cloud. And the AMI is typically just a single partition. It's not a full disk image. So the second sort of format we can spit out from Diskimage-builder is a full disk image where you've got a boot block and a partition table, and your kernel and RAM disk are embedded in it. And this is also kind of a necessity for non-Linux operating systems, things like Windows. But finally, we can also spit out just an ARI and AKI, so we get a kernel and RAM disk. And that can be quite useful for applications like PXE deployment, where you don't want a full image, you just want to get some software running on a physical machine, and then it'll do whatever you find useful. The point of Diskimage-builder is to be able to include your software into this thing. Just taking a base image from, for argument's sake, Ubuntu, and cutting it up into different bits isn't terribly useful. And so the OpenStack Deployment project, OOO, is heavily dependent on Diskimage-builder. We needed this tool to do what we're doing. We had a look around at the existing tools and couldn't quite get a good fit, so we ended up writing one. I'm sorry, I didn't mean to make more software. The database as a service project in OpenStack needs to deploy databases to a scalable number of machines. So they wanted to be able to use a really efficient process. They wanted to be able to test what they're doing will work and be confident it will work at scale. And they didn't want dependencies on custom package repositories within the cloud infrastructure. They wanted to decouple the testing and production side. So they also thought that what we're doing is a pretty good fit, and they're using that. Savanna, which is Hadoop as a service within OpenStack, also using it. And Heat are using it in their test pipeline, but as Heat is really itself a pure API, they don't use it in production. In production, they just have a web service, and they depend on the database. And one of the interesting things, when we started this, we were very worried about correctness, so we sort of assumed nothing. But we've learned that actually there's a lot of stuff we can assume, and it's not going to be generally true. But it's true enough for what we're doing, for the uses people are putting our software to, that we can get a more reliable and faster toolchain out of it. I'll come back to the specifics about these things. And if I don't, ask me at the end, in the question time. Yes, I know I said there wouldn't be any. So some other similar tools as a sort of contrasting thing. There's a thing called Oz, and it runs an operating system installer. We take an operating system and transform it. It takes input off the internet and mangles it and looks at your hardware and partitions and applies heuristics based on what you've got in front of you. That doesn't work if you're deploying a disk image to a variety of different sorts of machines. You have to do that code at the time you deploy, not the time you build the image. So we need to run that logic at a separate stage. Or we have to run the operating system installer, and we've just got away from that. The whole point of being able to deploy something is that you know it's simple and consistent. Kiwi, and my brain has actually gone and forgotten which one Kiwi is. I think Kiwi was a SUSE tool. Yeah.
Still is.
Right. Live build, again, that it's building a... so live build is actually the closest thing to what we're doing, in that it builds an image, but it was too Debian-centric when we looked at it, and we weren't confident that the sort of three different use cases we've got would be well suited and well accepted by upstream. Sadly, I have to admit we didn't really try hard, and if I was doing this again, I think we would. I want to try that much more vigorously. Lastly, there's a thing called Docker, which has really only turned up in the last year. And this is really, really, really cool. Who here knows about Docker? All right. So Docker is a container for an application, and it's built heavily on top of Linux containers and overlay file systems, neither of which we can use. But in every other respect, it's basically the same project. You want to create an image that's reliable, you want to be able to test it and deploy it, and so we need to figure out how we can engage properly and get some code sharing, or at least if we write a thing to deploy an OpenStack API server, we should be able to do that through Docker or through Diskimage-builder in the fullness of time. So why build disk images? I'm going to spend a little bit of time sort of talking about the background before I go into the plumbing. Hopefully I got the ratios right. When you're running at scale, either because you're running services for a very long time or a lot of services at once, or if you're in the really nasty place of running lots of services for a very long time, craft is going to build up and it's going to kill you unless you actively take steps to manage that. Google has a thing they've talked about that goes through and references a tree of what the system should look like and deletes everything that's different, just forces it into shape. And we're taking a similar sort of mentality. So you need some way, some arbitrary fashion of resetting everything to known good, get rid of the craft. And you need to do that while doing continual deployment. Nothing is standing still, code is changing, bugs are being fixed, and waiting 6 months for a release to get the bug fix you're suffering today isn't what you're going to do if you've got a production environment. It's what you're going to do if you've got a risk-averse environment, which is actually quite a different thing. So, continual deployment, the basic thing there is that everything you deploy, any change to your production environment, has gone through testing. Someone SSHing into the server and fiddling around to fix something really isn't an acceptable answer. It doesn't scale. You can't communicate effectively within your team that you're doing this to this one server if you've got hundreds of people in your admin team. So the initial deployment of a service onto a machine is actually a special case of the general principle that you automate the process by which you get software onto the machines. So what are the consequences of starting to do CI/CD? Everything, whether it comes from your software, your tree, or someone else's tree, application vendor, or operating system vendor, it needs to go through your CI/CD toolchain. That innocuous kernel update to add support for a USB key someone started producing in Asia might actually break your server. You don't know. You're dependent on faith if you don't actually test it. So the golden rule is that everything goes through CI, and you check that everything's running and working in CI, and then when you deploy it, you have a testing pipeline for deployment as well. That also means that package installation, adding a package to a server, can break functionality on that server. Not commonly, and you'd say, hey, but operating system vendors will make sure that can't happen. Actually, no. If their job is to provide customization and the ability to have, Postgres and MySQL installed by different users, then they can't predict all of the interactions that are going to happen. And if any of those things interact with your code, you can cause problems. So again, don't do that on a server-by-server basis. Do that on your cluster definition and propagate it through your pipeline. Load shedding, scale up, scale down, same thing. And the kind of big one, when you're doing a full operating system version upgrade, RHEL 5 to RHEL 6, Ubuntu 12.04 to 12.10, or 12.10 I think it was, yeah. It's got to go through the same thing. And the bit that I think a lot of people don't get is that really running apt-get or yum on a machine using vendor repositories is a bug in a continual deployment environment, because you're bypassing all of your QA. You're getting rid of all of the safety net that lets you do CD with confidence. So anyone who says, but I need to go in on that machine and install a package, is actually entirely missing the point. There are lots of ways you can solve these things. You could run a custom package repository. So for every change that you're going to bring into your environment, you create a new repository and you put the packages that change and would need into that repository, and then you do a big lock. I'm testing, I'm changing the repository, okay, deploy, pull from the repository, or maybe you copy the repository around so you can deploy while you're testing. You can build a lot of things on top of the packaging idiom to work around the fact it wasn't designed to handle this case. You can run lots of different custom repositories. Every machine change you'd go to Chef or Puppet and you'd say, please add this repository as a source for packages, then update all your packages, then do the config changes that are associated. You could put all of your different software into one big repository and use version locking. So list every single version of every single package and just update them in a config file as you go through. And that could be automated. But our general feeling about this isn't sustainable. It's not good engineering. We're keeping a layer, an abstraction layer, that doesn't fit what we need. There's a bunch of papers by people like NASA and Netflix about how they do cluster management at scale. And the basic thing is to have a file system tree which has exactly what you need. That's what you've tested, that's what you deploy, and when you make the change, you propagate it everywhere. Maybe incrementally, maybe you don't turn it all on at once, but it's not a human step-by-step thing, it's an automated, it looks good, keep the process moving approach. And the disk image is just a single nice wrapped up version of a file system tree. Why did we take disk images rather than actual file system trees where you've got lots of tools like rsync that are really good at moving file system trees around? And in fact, rsync has some patches to work with disk images, specifically with disk devices, but they're a bit experimental and it still wants to go slow at the big end. So, trade-offs. So images, an image repository has a very small number of keys. Even if you produce one per build, you're not going to go past 1 million in a short order. And a database key value store that can do 1 million keys, trivial these days. And the values that you have in there are pretty large, but again, that's actually a reasonably well solved problem. OpenStack has one, Glance, so we could just use that. And part of our mission, deploying OpenStack using the OpenStack tooling, is to use OpenStack components as much as we can. Because that way, as those components get better, what we can do with them improves and our life gets easier. We also provide a really good use case of we're doing something in production to the folk who are developing it. And from within the development community rather than from the user community. And we don't want those things to be entirely different, but there is some differences there. That's a different talk. We did look at doing package-based ones, so maybe we do some of those packaging options that I talked about. But Red Hat, Debian, or RPM and dpackage, two fundamentally different packaging systems, different repository formats, not to mention that there's variation within each sub-ecosystem. We want to support as many OSs, Linux OSs as we can, and if we try and use a single implementation, a new packaging system, Click or one of the ones that does a URL-based format, it's got its own complexity. We now have two packaging systems in the services we're deploying. We have the native one that we're getting the base OS image from, and we have the one we're layering on top. So we thought, look, let's just avoid that. Packaging is a super abstract thing. You can do anything to customize a machine with packages, and we don't need any of that. What we need is just the full tree, pull together, and deploy it. And as I said, NASA and Netflix have published papers, and there's a bunch of people I know in the HPCC space also say, hey, look, just get away from that. Wanting to control entropy also has some consequences. One of them is that you need to separate out the precious state, the data store, from the configuration and the software. Because if you replace the software on a machine, you don't want to replace the precious state, the data store. And when you replace the configuration, every time you want to assert it's the configuration that you want. You don't want to hope that it's configuration that you want. So ideally you have 3 different stores. Configuration that you write on a dynamic basis, but if you reboot the machine or throw it away, you just have it all go away. So var run kind of feels like a good fit for that. And you want your database to stay on disk if you reboot the machine or if you re-image it with a new software image. And your actual software image, you want to be immutable. There's no reason for anyone to write it or modify it when they're running, except when you're doing the building of it. And opinions may vary on this bit, but I don't think sysadmins should have home directories on servers. They should have them while they're logged in, and they should go when they log out. LDAP created groups or single sign-on of other forms, and your apt and yum databases, they're incidental to the operation of, for example, Nova. If you're maintaining your machines by using packages, they're incredibly precious things. If you're just throwing a new disk image over every time, they have absolutely zero relevance. You could, in fact, take them out of the image, and it would still work, but it's nice for people to be able to use dpackage to query what package version was installed. You don't want to lose that data. You just don't care about it being preserved across image push. Each image brings its own.
How do you feel about NFS-mounted home directories for that sort of stuff?
How do I feel about NFS-mounted home directories? I think that's an interesting way to add dependencies where you don't need it. If this is a machine I'm meant to do my work on, then I want an NFS-mounted home directory or a Ceph-mounted home directory so that I can have my data and be fiddling. If I'm going into diagnose a machine in a cluster that's got a wedge service, and I've decided I'm not just going to throw the machine away because I've got so many of them, it's cheaper to do that than to analyze, then I'm going to want some tools, but I certainly don't want all of my my work-related tooling coming along like that, not willy-nilly. Security ramifications and...
I guess I was thinking just for that environment.
Yeah, so, okay. So the follow-on question is like, if it's just that environment and you need a bunch of tooling. I think from a team perspective, if I've got a bunch of tooling, I need to analyze a server that's in trouble, I would rather bake that into the server so that I don't have a dependency on a service that might also be in trouble at the time I'm trying to diagnose this fault. Particularly when you've got services that depend on several other services to deliver them, like say a Ceph-based environment. You've got the Ceph components and then the machine I'm trying to diagnose. The machine I'm trying to diagnose is part of the Ceph cluster. I'd just rather have it real simple and separate. Sure. So Google's thing, an anti-entropy tool, we'll probably write one at some point, but I think we're going to get a long way with just having a read-only image, which we've just about got turned on in our environment, and none of the tools we knew of worked with images. So the ones we'd seen wanted a file system tree. We want one that will work off a disk image. Using configuration management, Puppet, Chef, great, do it. Don't use them to install the software because you're going back around and you're avoiding the whole thing about running apt on a machine. You're going to get into the situation where you need multiple repositories and it's going to be really, really hard. Use them to enforce the configuration, and the other problem with them is that by default, they don't delete everything they don't know about. They assert the things they've been told to assert about and everything else is kind of left alone. And that's really nice when you're turning Chef on an existing machine and you don't want it to trash it. But it's really bad when you want to reduce variation across a cluster. Across a cluster, you want to say, this is the entire state exactly as it's going to be. So what we did is we put the precious stuff on a separate file system. We've included the configuration in there for now, but we're asserting the full content of it every time. We blow away the root file system entirely when we deploy. We literally just copy new bytes on top of the hard disk. We probably will add an anti-entropy tool at some point as a band-aid, not as a band-aid, as defense in depth. And we expect people who deploy on top of OOO to use Puppet or Chef or similar things. Whatever they're using in their operational environment, they should still use. But we need to separate out the software installation from the configuration management for those tools for them. So Diskimage-builder itself, what did it need to achieve? As I mentioned earlier, the Debian, Fedora, SUSE, Ubuntu, building the images, both where we host the build and the sort of image we can build. So you can run a build for a rel cluster on an Ubuntu admin machine, or vice versa. You might say, hey, you only need to build machines in the cluster itself or in the production infrastructure. But people need to test things locally before they commit to them running in production. And if we had a same version lock, that becomes quite unfriendly for developer choice. So it was quite important to us that we had that flexibility. And it also makes it possible for upstream developers who are using Ubuntu or whatever to debug the problem people are having on building other architectures, and that is great for collaboration. We need to be able to build cross-architecture. I should say cross-OS then. Cross-architecture. So not everyone has ARM hardware, but data centers are starting to deploy out. Well, Calxeda's dead now, kind of. So there may be some sadness there, but certainly cross-architecture is in principle important, and we can do it using QEMU. It works. It needs to be fast. We're in the inner loop of CI/CD. If it takes us half an hour to build an image, your minimum test run is going to be half an hour, let alone deploy time. So we can build OpenStack images with all of OpenStack in them in about 8 minutes, and we haven't done all the optimizations we think are possible yet. So it's fast enough. It's not the fastest thing it could be. And if we were to do a whole bunch of aggressive caching like Docker does, we could perhaps make that even faster still. But you know what they say about there being 3 problems remaining in computer science. Cache invalidation and off-by-1 errors. And it needs to be debuggable. If you can't figure out what's going wrong, you're going to regret using this tool. So we put some effort into that. Sysadmin friendly, because sysadmins are going to be the primary users. And as I mentioned before, we need to build 3 different sorts of images. And there are the places they used. We met all of our functional requirements. They're there, it does it, it works, we're happy. If you've got the RAM, it will build entirely in a tempfs, which avoids a whole bunch of fsync. Lib my data, we haven't really tried to say, let's just use that. It might work, but we took a kind of simpler approach. If there is no moving platters to sync behind it, then sync is going to be fast.
Does it check the amount of RAM you've got?
Do we check the amount of RAM? Yes. If you've got more than 4 gig, it defaults to making a tempfs. Otherwise, it just uses /temp.
Right.
We aggressively cache the simple inputs that we can, tarballs from other places, Git repositories, and we've got optional cases you can turn on for the places where it's more complex, like PyPy. And you can also turn off cache invalidation, so you can run without going out to the web, nearly without going out to the web. Things like apt will still try, so we generally say, hey, run a squid cache alongside this. We use Ccache automatically. Brought in because when you download a lot of stuff off PyPy, you end up doing a lot of compiles. And we're doing a lot of compiles and bringing stuff off PyPy because we're trying to match what OpenStack Infra tests for upstream. The less variation we have from the upstream CI pipeline and the CD pipeline, the less surprises we get. So that's not a packages versus PyPy. They're both forms of packaging. That's a less variation equals how happy a lifetime. This break before or after and the stage thing, we're really happy with that. It drops you into a shell at the point where that stage is going to run, and you can just step through and poke around and see what the environment's like. From the outside, pip install Diskimage-builder. You get 3 commands: Diskimage create, ram Diskimage create, and element info. Diskimage create can create both the AMI, ARI, AKI style images or full disk. There's a VM element you put in, and that gives you the full disk version. RAM Diskimage create is what we use to create the Ironic and Nova bare metal deploy RAM disks or inventory RAM disks, and you can bend it to pretty much any purpose you want. So people have done some interesting things with that. Like, for example, you could have something that ran a bunch of stateless HA proxies entirely out of RAM disk using that. And element info is just an internal tool we use. It shouldn't really be part of the surface area, but it is. And that's what we use to get the diagnostics, the dependencies of an element. We have a whole bunch of stock elements in that tree, and the whole point of this is that you get to write your own. So, an element encapsulates the installation of software from deb, rpm, npm, pip, whatever. Configuration. If you're using heat, you're going to want something in the element to take heat metadata, which is a JSON file on disk, by the point you get to it, and write it down into config files. You could use be using Cold Fusion or Chef Server or a Puppet Master, and you could be using Chef or Puppet in the image. So the element itself needs to abstract that. We don't want to be thinking about that cross-element, or at least not too much. And it also needs to encapsulate data upgrades. If you're keeping your precious data, your Postgres files across image pushes, you need to have something that will do a Postgres 9.1 to 9.2 migration for you when you've pushed out the new version of the software. And it's a combination of procedural and declarative stuff. So when we start everything, we just write it as procedural code. Shell, it's very good for running a series of commands. And when we start realizing there's a pattern there, we turn it into something you can declare. So you can just say, here is a file on the top of my element that says, these are my dependencies, and we now spider across that to bring in all the elements. That wasn't there in the beginning. And generally, we'll leave the backwards compatible procedural way in place so that we can move forward. The flat namespace thing I think is kind of important. We thought about how do you model these things. Do you have a namespace like Java does, my organization, your organization, or do we just have a path and we take the first one, and if you want to take different precedents, you put them in a different order? I'm sorry, Josh, could you not talk? It's really good acoustics here, so I can hear everything. Finally, one of the basic goals we've got is that you shouldn't have to change the core code as a user to add support for a new operating system or a new way of doing things. So as much as possible, we have a super thin framework that then calls out and might get variables back or whatever. And it's been reasonably successful. Certainly the SUSE support was able to be added without changing the core. I think we found one bug, latent bug.
There might have been something funny in the shuffled around the C cache thing slightly.
Yeah, so there was
something was trying to be unmounted a few more times than it should have been.
Yeah, Tim was just saying there was a bug with unmounting, and the C cache support wasn't quite right. In fact, the C cache support is one of the places we haven't pushed this entirely into user space. It's still in part of the core. So that's a work in progress. The image build proceeds through a set of hooks, root.d, preinstall.d, install.d, etc. And that hook, like the root.d, that hook is run across all of the elements at once, and then we move to the next hook. And for all the elements, we run their pre-install code, and then for all the elements, we run their install code. So you can do cross-element configuration by injecting data somewhere that another element needs by doing that in the phase before or a lower numbered script. You parameterize an image build by including elements, and they're simple. Within each of these hook directories, they're simple executable files. So again, sysadmin friendly, very easy to reason about. Sadly, multiple OSs don't have the same interfaces. Not everyone has dpackage, for example. They should. And
Just a comment, in the LSB, RPM is part of the LSB, so if David would be offended, I guess, but if they implemented that, then you really could have one package manager.
That would be the ideal world. So we've got we've abstracted that out. We've created a little, guys, time out. The question was, the LSB defines RPM as the interface. You could just use RPM. I don't think the LSB defines yum yet, and we need to be able to grab the packages over the wire, not just do the local install operations. So we have our own little wrapper. Maybe the LSB will adopt that. Install packages. It installs packages. And so generally we've tried to pull things out into a common abstraction point that you can then, in the operating system specific element, you provide an implementation that matches the contract. And for debugging, caching, tilde.cache, image create. We haven't had problems with the cache size being too large yet, but I'm anticipating some people will eventually find that and they'll just delete their .cache, so yay. I want to walk through in detail the Ubuntu element just to give you a sense of the sort of code we end up writing and how much complexity there is. So this is the README file. It just tells people how to use it. We use Ubuntu Cloud images, and it's the baseline. You can override its behavior by exporting a couple of environment variables. Now, longer term, I want to move from environment variables to having a unified JSON data dict that we can pass in at the command line, and every element can just consult. because I don't think using environment variables is a particularly good user interface. It's hard to introspect it, it's hard to see what's there, and there's too many shell injection attacks that have been done through environment variables for me to be comfortable saying, hey, this is going to work well indefinitely. The element deps file. This lists the dependencies. We depend on case URL, dib run parts. By the way, you'd think standard commands like run parts are standard.
That was another one that we had to
Yes.
go around.
So in fact, run parts, we were using run parts in the infrastructure, and the version on Red Hat and on Ubuntu or Debian, etc., was sufficiently compatible that worked. But then on SUSE, it just wasn't. So we had to use the one we'd done for in-instance stuff everywhere. So that was another patch. DKMS is another element that the Ubuntu element depends on, and dpackage. Now the dpackage element doesn't install dpackage, it contains the install packages abstraction layer for dpackage. Can you guys read this? No. Okay, /bin/bash. Can I read this? It says these are useful things, but not harmful for all the images we build. It does set-EU, and it checks that an architecture and a target root have been set. Then we do a shop-x glob. I can't remember why we do that. And then we set a bunch of environment variables based on the input. So we're looking down here, we're looking at the cloud images.ubuntu.com is where we're going to download from, but maybe you override that to a local mirror you've got. We're going to build Saucy unless you override that. We calculate the actual tarball path we're going to need and where the SHA sum for that's going to be. Note that we use HTTP for the image, but HTTPS for the SHA. So we can cache and download over a cache the image, but if the SHA is secured. And the cache file path we're going to write the image to on local disk. Then if we're in offline mode, we let the user know. We're not going to actually try and invalidate it. Otherwise, we download the image using the cache URL helper, which downloads and caches on disk for us. We pop over and we check the SHA sum, about halfway down this page now. And then just a couple of lines of comment, extract the base image, and host. We use numeric owner when we extract it because, different operating systems, in fact, different installs of the same OS may have different UIDs. And we create when we untar it into the image we're building. So we've had a directory made for us by the infrastructure, and we're untarring the contents of this image into that. And finally, we delete the lost plus found because at this point we have a directory on disk, not a file system. Lost plus found isn't appropriate at the root of that. We had a bug that caused us to add that in. I don't remember what it was. Sorry. It turns out that the app Zappian index package in Ubuntu is horribly buggy. The question was, who would have thought it? Well, if it was buggy and supported by standards, I would have been surprised. But this is actually a standards violation for Debian. So what happens is when you install it, it starts a background thread to update the package database index. So you've got full text indexing on all your packages. Of course, we generally do this, and then a few seconds later we copy the thing to another place, and then we delete everything. And it turns out that you can't actually delete things properly if they're in use. Like you can delete the inode, but the inode stays pending.
Finish your sentence, please.
I have. The inode stays pending, full stop.
Just out of curiosity, why exactly did you conclude you had to write your own abstraction layer on top of package management when something like Puppet already does that for you?
Because there's a huge Puppet community and a huge Chef community. That's exactly why.
And now we're going to have a
Wait,
Puppet
no.
and a Chef and a Discord.
No. So we have a very thin layer, and we expect people to layer Chef or Puppet on top of it. The abstraction layer for installing packages is 25 lines of code. I will bear that on my soul happily. The abstraction layer for doing configuration management and Puppet and Chef is much bigger than that. Fine. Configuration management, that's a much more interesting problem than installing the packages. So I see it as the Puppet and Chef do too much. maybe we have a beer after this. We also remove grub because we don't actually have a physical device at this point. We're just in a directory tree in /temp. Trying to install a bootloader from there is not going to do the right thing, or if it does the right thing, it's going to be the wrong thing. And the reference image we downloaded from Ubuntu doesn't actually have physical hardware drivers, but we're going to be installing onto machines with physical hardware, so we install the hardware-specific driver package, which is Linux image generic. There's other, note this is an install.d file, so this runs in the install.d phase. This runs in pre-install.d, and this was running in root.d. So root.d is responsible for creating the root image. The pre-install runs before the install, and that means that anything in install can assume a good environment to do operations from. We also let you customize the block device, cleaning up, extra data, and post-install. And the difference between post-install and cleanup is that one runs in the chroot and one runs outside of it. So if you want to do meta operations, you can do that from cleanup. We have some RAM disk specific ones, binary dependencies. We'll copy in a single file, so you build a very thin RAM disk. You don't want your package database in there, for example. Init, we want to run something as part of init in there, and udev lets you poke at udev rules. I mean, again, you could do it all procedurally. This is just abstractions to be useful. On the interior, it's about 130 lines of code in Python, and about 3,000 lines of code split between the framework, 1,000 in the framework, and nearly 2,000 in our elements. And that's in Bash. And Bash versus Python, it's longer in Python to do this. Python is not a good abstraction for run a series of commands. I've seen lots and lots of attempts to do that in Python, and none of them give me confidence. Bash is battle tested. We trust our inputs. I said earlier we make some assumptions that aren't generally true. It's not generally true that you can take a disk image, mount it, and be confident that your kernel hasn't just been rooted through a file system injection bug. But we're building a disk image to run our infrastructure on. Guarding against the person who gives us the image containing the binaries that we're going to run as root on our hardware is a false sense of security. So we said, look, let's be clear up front. This is going to be able to compromise things. That's fine. If you want to run this as a service for someone else, you just wrap the whole thing up in a VM. That's your abstraction for security. And people have done that. We build it in a chroot. So we start with that empty directory. We do the operations in the chroot in the directory. And we have to bind mount procsys and dev. In principle, procsys and dev from your outer host being different to the operating system on the inner host is a real big problem, and you should never do it. Again, it's one of these assumptions. In practice, it works just fine. Initial content, we have to make sure we don't actually run services while we're building the image. We don't want PostgreSQL running while we're building an image that will contain PostgreSQL. So we hobble that on Debian machines and on Red Hat machines. Installing something doesn't run it, which is actually in a lot of ways a much better default, in my opinion. So we don't need to do that there. We install all the software. We then create a big sparse image file, make a file system in it, copy the stuff in, unmount the file systems, remount them, create a bootloader, and then shove it all down into a QCal2 file. Right, so things we could do better as a distro. Don't start services on installation. It's absolutely true that when someone is managing a precious Snowflake machine and sitting down in front of it, that when they install it, they want it running. It is never true for anybody running automated systems or clusters.
We already do this in image builds on Debian and Ubuntu anyway.
Steve is saying we already hobble it on image builds on Debian and Ubuntu, and it's true that that is the case. The policy-specific way of doing it doesn't work. All the tools actually do it a different way. So we could change policy to say that you don't start things when you install them. Because, as I said, that does not work. Yes, we filed bugs. People do not respect it well enough. Deal with it. The point is, though, that if you have Chef or something, when you install software, Chef wants to customize the configuration before it runs it. So anyone who's doing automated system administration does not need installing starts it. We need to think more about clusters as a design element. Single machine, standalone in the corner, the only one doing mail is no longer the default. The default is an HA pair with a shared network store for the mail and backups. So we need to think at a higher level as we put together our policies and our tooling when we make that consumable for users. We should move to an image-based delivery ourselves. And we should update those images in a graceful way. Ubuntu has started doing this with its phone project, and I'm really excited to see where that goes. And we should standardize some more interfaces. The LSB might be the right way to do that. They haven't been super successful at getting everyone to really deliver, but maybe we could just come together and do it ourselves. Specific ones we've noticed, installing a bootloader after the OS, like when you upgrade it. At the moment, install the package upgrades the bootloader, but anyone doing images or anyone who's moving hard disks around their machine or dealing with a failed hard disk actually needs to do it outside of the package install. So it'll be really useful just to be able to have I want a bootloader on this disk, you know the details, you're the OS, please make it happen. Instead of having to know the grub2 or some other tool. File system permission bit resets. By that I mean SC Linux. But any other tool that wants to do stuff on inodes on a pervasive fashion, discretiacles or something like that, provide a single interface to reset that across the whole system to policy. Package installation and package names. Really? Last year I gave a talk about the big picture of the thing we're trying to do. I said we're going to try and do disk images and we're going to do this and that. And someone came up to me afterwards and said, don't use QEMU MBD, it's terrible, it wedges machines. They were right. But it turns out that only a small amount of care is needed to remove all of those cases. So we got that under control, and we don't use it during the image build now. We do when we pull out the RAM disk and kernel, but a small change to what we're doing will allow us to fix that. We've got an open bug. Our first implementation just started with a QCal2 image and did all of the operations in that, and it turns out that actually QCal2 is not that fast. It's a lot faster for us to start with a sparse raw image and do one QEMU image convert than to do all of the operations in QCal2. I'm running out of time. I'd love to answer the question. I want to wrap this up, though. Initially, we had to manually set a partition size. Like we had to say, hey, 5 gig. It turns out that users are really bad at guessing that. So we now auto-guess, and it's not perfect, but it's a lot nicer. And I was just saying, run parts. Wow. So the run parts in Debian is C. It's got a lot of features. It's really nice. It does parallelizing. The run parts in Red Hat is 5 lines and doesn't do anything. And the run parts in SUSE was worse.
It didn't even exist. We didn't use it as part of our init system.
Right.
So it wasn't there.
Yeah. There is another one in Red Hat you can install, but it's different again. So we have our own, which is Python. I think it might be Python, or it might be still just shell. Anyway, and one thing that was a bit surprising is I kind of thought of MakeFS as something that people would make good. But it turns out, I think it does 8 gigabytes of I/O to make an X3 file system that's of a terabyte kind of size. That's a lot of I/O when you're doing that over the network. It's a lot of I/O when you do it inline in a test. And by the way, all that I/O is writing zeros. So X4 is lazy. It says, I'm going to have some inodes here and set them up when you're actually mounted the file system. It's a lot better. So be aware, MakeFS may not be free. And I think I've got 0 time for questions at this point.